Hi everyone, welcome to the second video on the Klein-Gordon equation. In this video we're going to look at the charge degree of freedom that's buried within the Klein-Gordon equation. We're going to explore the two-component formalism, which leads us to a Schrodinger-like equation, except it's not manifestly covariant anymore. And we're going to look at the non-relativistic limit of the Klein-Gordon equation in that two-component formalism. And then we're going to discuss charge conjugation, which brings us around back to the charge degree of freedom again. So it might take a little while, so let's get started. So let's just recap again what the Klein-Gordon equation is. So that's the Klein-Gordon equation in one of the ways that we wrote it in the last video. So now, if we have a look at this equation, and it's easy to show that if psi solves the Klein-Gordon equation, then so does the complex conjugate psi star of x, provided we also take the electric charge E to minus E. So it's clearly that, let's just leave that as homework, but it's kind of clear if you just take the complex conjugate of U and E goes to minus E simultaneously, you'll see that U is unchanged. So this is kind of a curious result, but it leads us to start thinking about, well, what is the charge degrees of freedom which are inside the Klein-Gordon equation? So let's continue now. If we take a solution, well, last week we found the solution of the Klein-Gordon equation if we have no fields. So we can do this without fields. And you can do it at home with fields if you want. We wrote the forecurrent as J mu equals I over 2m psi star d mu psi minus psi d mu psi star. And if I just want the density with no fields, which is enough for me right now, then I will substitute my psi plus or minus into J naught, and I will get density plus or minus is equal to plus or minus EP over 2m. Oh, that's not factor 2 anymore, my bad. EP over m, psi plus or minus, psi plus or minus. If I start with this density, then in order to get a charge density, all I have to do is multiply this by the charge of the particle. So E could be positive or it could be negative. And EP is the energy is defined to be positive, right? So what this means is that the psi plus particles have an effective charge plus E, but the psi minus particles have the charge minus E. And generally, the general solution of the Klein-Gordon equation is going to be a linear combination of both types of functions. So the Klein-Gordon equation, even though it was written down before we knew of any spin zero particles, we now know that this is good for a whole host of composite particles, such as pi plus and pi minus, the pions. And we can see that if we have a wave function which describes the pi plus, then the complex conjugate of that wave function will describe pi minus. So the Klein-Gordon equation includes a charge degree of freedom. What about neutral particles such as pi naught? In this case, we can take a linear combination of both of them. Let's have a look at how that works. We've got the density is now going to be I over 2m psi star d psi dt minus psi d psi star dt. And we want that, in the case where this is going to be a neutral particle, to be equal to 0. So in other words, for a neutral particle, we expect that the density will be 0. And so that means that that will be true if the wave function is real. So what we can do is we can take a linear combination of pi plus and pi minus such that we get a zero charge linear combination. So for example, we could take psi plus for some positive momentum plus psi minus for some negative momentum. And remember, that will lead us to so psi minus for the minus p is going to have kind of a positive kinetic energy. So it's be like a plus p. So if we take a linear combination of these two, that's going to give us a neutral particle. So the Klein-Gordon equation has within it extra degrees of freedom. That is to say that for every momentum p, we can find three independent solutions, or three solutions corresponding to charge positive, negative, or 0. The next thing we want to look at is the two-component formalism. So we've got the Klein-Gordon equation, which is a second-order differential equation. The point is that any second-order differential equation can be written as two coupled first-order differential equations. For example, we could take the wave function and the derivative of the wave function as the two variables, and then if we specify both psi and d psi dt at some point, then we can actually extrapolate that to the rest of time. What we're looking for ultimately is a equation that's Schrodinger-like. So what we want is something that looks like this. I ddt of some big wave function psi is equal to h psi, a Schrodinger-like equation. So now we can do that, but now this big psi is going to be a vector in C2 space. In other words, it's going to have two components. So what we'll do is we'll define, instead of using just plain old psi and d psi dt, what we're going to use is these two instead. We'll define phi, which is going to be a half of psi plus I over m d psi by dt. Remember, little psi here is just the solution of the Klein-Gordon equation. And chi is going to be 1/2 of psi minus I over m d psi by dt. So we're going to use this to break up the Klein-Gordon equation. And if we look at these two, then we can see straight away that if we add them together, we get psi equals like phi plus chi. And I'm going to get confused saying the psi's and the chi's and the phi's, but bear with me and hopefully I'll write down the right thing even if I say the wrong thing. And if I subtract the two equations, then we'll get I d psi by dt is equal to m phi minus chi. And this might be one of those rare occasions where I put back in the h bars and the c's. Let's go back to our density equation. So if we look at what happens to our density now, we write density is equal to I over 2m psi star d psi by dt minus psi d psi dt star so now we expand this out and we're going to get phi plus chi conjugate. The psi by dt is going to be minus im times phi minus chi minus phi plus chi times the conjugate, which will be im times phi minus chi conjugate. And that is equal to minus I blah, blah, blah. So that'll be a half. Hopefully I get this right. It'll be phi star phi, multiplying out the first term here, plus chi star phi minus phi star chi minus chi star chi. And then the second term is going to be minus phi star. And it should have a minus sign there as well. Oops, so plus. No, it's correct. So it's just taking out the minus I. Okay, yeah, makes sense. So plus phi star minus phi chi star plus chi phi star minus chi star. And cancelling out all the terms, we're going to get just phi star phi minus chi star chi. So it looks particularly nice to have the density in this form. And we see again, as we expect, it's not positive definite. The phi's give us a positive contribution to the density and the chi's give us a negative contribution to the density. So this already gives us a hint as to where we're going. Okay, how do we express the Klein-Gordon equation in terms of this phi and chi? So back to Klein-Gordon equation. If we write these two equations instead, we write I dt phi. Remember, dt is just going to be the 0th term of d mu that we wrote last time. And I introduced this notation here. That's kind of an obvious one. What it means. It's just to remind us that if we ever need to go back, which we will soon, to having the electromagnetic field in there, then we know exactly how to do it. So these two equations, these are equivalent to Klein-Gordon. How do we know that? Well, I'll leave that as homework. And if you want a hint, then I would say subtract one from the other, and you will quickly come to the Klein-Gordon equation itself. Okay, so we've got these two equations, which I tell you are equivalent to the Klein-Gordon equation. And what we want to do is you want to take these phi and chi, and we will couple them together into the big psi that we had before. So couple these functions into a vector. I told you it was going to be a vector, and here it is. Psi is equal to phi chi. Look, it kind of looks like a spinner when I write it like this, but it's important to remember that this is not a spinner because it's not in spin space. This is in some other space, something like charge space. Okay, so this is going to be a two-component spinner, not a spinner, two-component function. And what we'll do is we need to write down something that looks like the Schrodinger equation now. So if I look at the coupled equation that I've got up at the top of the page here, then I can see that if I write down on the left-hand side I dt of big phi, so this is writing down both equations at the same time, okay? Equals minus 1 over 2m d squared. Now I need a kind of a matrix in order to have something like this. I want to have positive on the top row and a minus sign on the bottom row. So if I write that, it gives me what I want for the first term. And for the second term, I want the top one to be proportional to chi, and I want the bottom one to be not minus. So if I write down something like this, it gives me what I want. So I've just written down the two coupled equations as one equation, but really it means two equations because there's two terms, the upper and the lower components here. And then because I've now got these 2x2 matrices, I'm just going to reach into my bag of 2x2 matrices and pull out any 2x2 matrices that I know the properties of intimately. And so if I think about 2x2 matrices which span all possible matrices, I'm going to go straight to the Pauli matrices. So now I'm going to take this one, and instead of writing it in some fancy way, I'm just going to write it as minus 1 over 2m d squared. This is going to be tau 3 plus I tau 2. And these are just going to be Pauli matrices, but I'm writing them with a tau because I don't want anyone to get confused that these are spinors. And these three matrices plus the identity matrix will span the entire four-dimensional space that I need. So this is another way of writing it down. And now I've got something that looks like a Hamiltonian. It's simply I dt psi equals h psi I've lost m. I need an m here and I need an m here. And again, if I start with this equation, I can easily show that the Klein-Gordon equation is satisfied. What I would do is I would write I dt minus hf psi equals 0. And then I'll multiply that on the left by I dt plus hf. I apply it to both sides, but obviously when I apply it to 0, I get 0. All these are operators. Sometimes you have to put them back in, just remind yourself. And then if we expand that out, and noting that hf and dt commute with each other because, in fact, they're the same thing, I can expand this and say minus dt squared minus hf squared psi equals 0. So what's hf squared? Hf squared is equal to, it's a matrix equation, right? So we've got hf, it's over here. Let's actually have a look at what it is if we expand it out. It's nothing but this. Minus 1 over 2m d squared plus m minus 1 over 2m d squared plus 1 over 2m d squared, and this one's going to be plus 1 over 2m d squared minus m. I want to square that, and when you do that, you will find it's equal to minus d squared plus m squared, 0, 0, and minus d squared plus m squared. So you want to check that at home. And that's equal to minus d squared plus m squared, which if I substitute it back into the equation here, I will get minus dt squared plus d squared minus m squared times big psi equals 0 minus d mu minus m squared psi equals 0. And so therefore d mu plus m squared applied to phi and chi equals 0. So this is actually two equations, and what this shows is that each component, phi and chi, each separately satisfy the Klein-Gordon equation. In other words, both the upper and the lower components are solutions of the Klein-Gordon equation in and of themselves. So we've got a representation now of the solution as a two-component vector. What does the density look like in this particular case? So in this representation, In this representation, the density rho is equal to phi cross tau 3 phi. Why do I say that? Well, phi cross is phi chi, written like so. Tau 3, 1 minus 1, 0, 0. Phi itself is just phi chi. And so that's equal to phi star phi minus chi star chi, which we all agreed was the density. So we have this way of writing it, and just in order to make connection later on with the Dirac equation, we can also write that as being phi bar phi, where phi bar is defined as being phi cross times tau 3. Now, I'm not going to go further with that, but I just want to show you that then in this, if we use this definition of the bar, it's hard to see it with this drawings, but maybe I'll clean that up later. This phi bar here is, if we use that definition, then this density here looks pretty much like what we expect from the non-relativistic case. In other words, in the non-relativistic case, it was just psi star psi, and now we have something which is psi bar psi. So it looks very, very, very similar. Okay, I don't want to keep those around there. So now we've got the representation, and now we want to write down plane waves. We write phi is equal to some constant a, phi naught chi naught. These will not depend on r and t. They don't depend on the position in space-time. They're just going to be constants because it's a plane wave. So this is, again, just an ansatz that we're going to now use. We're going to substitute this into our formula. So we substitute that into our formula, and we will get derivative with respect to time is going to pull out a minus IE. So this is nothing but E times phi naught chi naught. The exponential part the phase part is going to cancel out on both sides, as is the overall normalization constant. I write this one as minus d squared is just p squared. So we've got p squared over 2m. We've got phi naught plus chi naught plus m phi naught. That's the upper component, and the lower component is minus p squared over 2m phi naught plus chi naught minus m chi naught. So that's our equation. And if I just pull out the chi and phi, I will get p squared over 2m plus m, p squared over 2m. This is very much like what we wrote before, minus m times phi naught chi naught. So this equation is now an eigenvalue equation for phi naught chi naught, which are constants, right? They don't depend on position. So what are the eigenvalues of this equation? Well, you can do it formally if you wish. Maybe that would be a good thing for you guys to do yourselves. But there's going to be two eigenvalues. E is going to be equal to plus or minus the square root of p squared plus m squared, entirely unsurprisingly, which again we're going to call plus or minus EP, where EP is the positive one. So that's the eigenvalues. And again, this is just an eigenvalue equation, so involving matrices, so you guys can actually go and just do it yourself and just check that what I've just said is correct. What about the eigenfunctions? Again, it's homework, but if we take E equals to EP, that's a positive one, then we've got phi plus is equal to A plus EP plus M, M minus EP, E to the I, P dot R minus EPT. So that's my eigenfunction for the positive solution. What about for the negative solution? Then I will find that the free wave function is M minus EP, M plus EP. Plus EP, T here. And you can check these by substituting into the wave function up here. Okay, what about the normalization constants? What we're going to do is we're going to normalize these by saying we want we want the integral of psi bar psi, remember that's the density, over all space, not time, is going to be equal to +1 for the positive solution. So that means that I want my integral of phi star phi minus chi star chi equal to 1. That's over all space. So that's a plus squared times the integral of EP plus M squared minus M minus EP squared over all space is equal to 1. And okay, now I need to understand what I mean by all space here. So if I assume that I've got some kind of a box or some kind of a constraint, anything the size of the universe, something which is going to give me a volume, then I will say that A plus squared times the size of that volume times 4MEP is equal to 1. So that volume can be whatever I want it to be. It's a box normalization. Is it the size of the universe? It's something. And so then I can define A plus as 1 over 2V square root MEP. So, and you can actually do that for A minus as well, and you'll get the exact same result. And typical value for V is 1. And in any calculation that you actually do, any observable, you will be integrating over all space to find that observable. When you take your bracket and you put them together and you integrate over all space, and then that's going to cancel with this normalization factor 1 over V, so that you get a so that you end up having the v drop out. I just realized I've made a mistake with the v, so it should be underneath the square root as well. So let me fix that now. So v drops out when calculating observables. We can set v equals 1, for example, without any loss of accuracy. So let's go back and have a look at these wave functions. What happens to them in the non-relativistic limit? In the non-relativistic limit, we write EP is equal to the square root of m squared plus p squared. By definition, that is approximately the same as m plus p squared over 2m, and we can do extra terms as we wish. So with that expansion for EP, we can then say that m plus EP is something very close to 2m, and m minus EP is something very close to minus p squared over 2m. And so then, if I look at my positive energy solution, it has non-relativistic limit approximately 1 over 2 square root MEP times m plus EP m minus EP e to the I p dot r minus EPT. And in the non-relativistic limit, that's going to become something like 1 over, so that should be an equal sign, equals. So in the non-relativistic limit, that will become 1 over 2m, and then minus p squared over 2m times the phase factor. Which is 1. And then if I go p squared over 2m over 2m, it's something like minus 1/4 v squared, which is v squared on c squared, right? And I'm putting the c squared there. Minus 1/4 v squared on c squared times the phase factor. So the upper component is 1. And then the whole thing looks like a non-relativistic particle phi. And then the lower component is order v squared on c squared. So if velocity is small, then that part is very small. On the other hand, my negative energy solution, what does that look like? Phi minus is something like 1 over 2m times minus p squared over 2m. It's exactly the opposite, right? Either I p dot r plus EPT. And so that one has a small upper component and a large lower component. And so if the upper component phi is large, so this one's something, this upper component is large, then this is like phi, and then we don't have to worry about the lower component. Yeah? So that's the non-relativistic limit. On the other hand, if we have the negative charge particle, we would say that the upper component is very small and the lower component is important. Yeah? So the upper component corresponds, as we know already, the upper component corresponds to the particle and the lower component to the antiparticle, which is exactly what we expected from our discussion of the density when we first introduced the two-component formalism. Okay, the last thing we want to do is actually talk about charge conjugation. So we've already found out that if I take psi minus p, and I can write that one as, remember A was the same for both of them, right? So A, m minus EP, m plus EP. And now, because I've got that minus P in there, I can write it like this. Yeah? So this is, if we have a look at this equation here, psi minus, but for minus P instead of plus P. It's m minus EP on the top, just as it was before. And now, what I want to do is I want to take I want to say that that one there is equal to A m minus EP over m plus EP times e to the I p dot r plus EPT. And I want to say it's this thing conjugated. And I've swapped the upper and the lower components. So if I take T1 times psi plus positive P, and then I take the complex conjugate of that, I find that they're equal to each other. So in other words, I swap the upper and the lower components with T1, with tau1, this one here. I swap the upper and lower components, and then take the complex conjugates. So what is this operation I've just done? It's a charge conjugation. If psi represents a positive charge, then psi charge swapped, the conjugate, is defined as this thing, which is equal to chi cross phi cross, star. I've just changed the way I've written the phi, so I'll change that back again. So that describes a particle with negative charge. And it works both ways. Since psi, if I complex conjugate that one, then I get charge conjugate. I keep saying the wrong words. It's a charge conjugation. I get tau 1 of psi star, and that's nothing but psi. I know that because my Pauli matrices all have the property that, this property, right? But we know that. So, in other words, well, we also know that psi c satisfies, because we already proved it, the same equation as psi, except we need to take EA mu goes to minus EA mu. So in other words, we have to swap the charge. Yeah? But we already knew that, and you can check that yourself. And perhaps we should check it ourselves. Let's check it. So we'll start. I dt psi is equal to minus 1 over 2m d squared tau 3 plus I tau 2 plus m tau 3 psi. Now I take the complex conjugate of that. Remember, I have to take the dt star as well, because that could include a plus IEV. Take the complex conjugate of this one. Take the complex conjugate of this one. I know already that the complex conjugate of T3 is T3. Or maybe I should put it in there anyway, just so that we know what we're doing. And then I'm going to multiply by tau 1 from, in fact, it needs to be minus tau 1, doesn't it? Because I need to cancel out that minus 1 as well. So let's actually do that one as well. So multiply it by minus tau 1 from the left. And so that will give me an I, that will commute, I dt star tau 1 psi star, which is what I actually want, equals. And now I'm going to have to watch all of my commutation relationships. But good thing is I already know how to do all of those. Oops, that should be a minus I. No, it shouldn't. It should be plus, because tau 2 star is equal to minus tau 2. So that actually stays the same. Plus m tau 3. Oops, that should be tau 1, tau 3. Making so many mistakes today. Psi star. And that is I dt of the charge conjugated version is equal to 1 over 2m. Why have I got rid of that? You'll see it in 1 second. That's d squared star. Tau 1, tau 3 is equal to minus tau 3, tau 1. And same with tau 2, because all the Pauling matrix is anti-commute. So what I want to do is put all of those together, and I get tau 1 psi star, which is, if I see again, right? And so again, we can see just, this is actually the end of the proof, right? It shows that if I take d tau to, or d mu rather, d mu goes to d mu star, which is the same as taking EA mu goes to E minus EA mu, then I get back to the original Klein-Gordon equation. So charge conjugation turns a negative energy state with momentum negative p into a positive energy state with the opposite charge and momentum plus p. So that's the charge conjugation, and it starts to, and it's inside the Klein-Gordon equation. Okay, well that's enough for today, and we will pick up tomorrow with the Dirac equation. Have fun.